Yeah, it's working.
Jo, to možná dobré.
Že bychom jako tohle uzavřeli proto, ať tady je to, protože jinak to nepůjde vidět. Okay. Ladies and gentlemen, please, we will start very soon, so I will also ask you to, for now, for the presentation, stop the bar, because the sound here is not the best. So in order to actually hear the presenters and hear everyone that will be sharing the ideas and knowledge today, please be respectful in that sense. Thank you very much.
Good evening, everyone. I would like to welcome you here on Faculty of Architecture. As you might know, this week is the week when all of our students of architecture, urbanism, landscape architecture and design finish their projects, finish their one semester hard work, and they exhibit the work here on the faculty. So I would like to start to invite you to this exhibition and see the work of our students. Before I go on, I would like to heartily welcome one lady, and I have to say it in Czech because I don't know how to translate it, but it's ředitelka odboru vysokých škol MŠMT Karolína Gondková. I'm very happy to welcome you here. Our faculty is very proud to have the best architects and designers from the Czech Republic, and we are very proud that one of our faculty members now is Maas, who is not from Czech Republic, but who accepted the role of being the visiting professor. And before I hand over the floor to him and his students to present the result of their work, I would like to say a few words of thank you. First, I would like to thank our students for the enormous amount of work they did during the semester and for their courage that they applied to the studio, which works a little differently than maybe our studios on our faculty. And they also have to present the work in front of all of you, which I think is that you need a lot of courage to do that. I would like to thank very much Winnie and his team from the Y Factory, Javier Fernandez, Shimon Knetik, Adrian Ravon, and Lex Telu, who devoted a huge amount of energy to our students. And finally, I would like to thank the Embassy of the Kingdom of the Netherlands for their auspices and support. And I would like to briefly give the microphone to Martina Váchová, the representative of the Embassy. Thank you.
Thank you, Mr. Dean, for the floor. So first of all, let me just excuse Mr. Ambassador that he couldn't join us tonight, but he's very much eager to see the work you have done, so he will definitely come here to visit the exhibition. And secondly, I must say I'm very glad that I could step in his shoes and be here tonight, because I myself was very lucky to be able to actually study urban and regional planning in Amsterdam, so in the Netherlands, in the Mecca of urbanism and architecture. And I'm sure that Therefore, it's an honor for me, on behalf of the embassy, to welcome here the very first visiting professor that is from the Netherlands and the renowned architect Maas. And I'm glad that the Faculty of Architecture put in effort and started this cooperation. And I'm sure that Maas has been, for each of you, the students of his studio, an amazing source of inspiration. And at the same time, I believe that you were also inspiration for him, and that the exhibition will inspire the others, everyone who is here tonight and who will see it in the next days. I have heard that it was quite demanding, the work and the effort you have put in this. At the same time, I'm sure it was very rewarding, and it is very rewarding for you to see it put all together tonight. So thank you all the faculty and Maas for and your assistants for all the work, and also the students, and I wish you good luck. Thank you.
Thank you. Thank you that you're all here to start with. I think this is, and I want to say also immediately that this is not kind of exclusivity, that I hope that you all, everybody here in the faculty, takes also this opportunity that this building offers to speak out loudly together and to communicate with each other about the future that architecture needs and deserves. It is, it's more difficult than a couple of years ago, with different crises, from European crisis to climate crisis to wars, and then somehow we can behave innocent and hide like ostriches our thoughts into the ground, and you see a new generation coming up that needs actually more strength and more support on that and more direction. So I hope that to all my colleagues, that this is an invitation. This is not a temple of luxury or like somehow like star behaviorship from my side. I apologize immediately for that. It's only a way to invite you all in. I thank indeed Dalibor. I thank Irena, I thank Andrea and Olga to invite me and us in it, and to work with you during the last semester to start with it. And what was the plan of such a year that we have? Observing a situation, like I said before, about a world that is changing, about a faculty that is concentrating a lot on the very precise issues of the Czech Republic with all the beauty and its respect. I thought it might be nice to add 2 design tasks this year on the agenda. One, instead of designing a house, can't we design the world? And you see it today as one attempt to understand the world as an object of design, which is ridiculous, of course. But on the other hand, it has led, I think the students will talk about that, to a cohesive, if not holistic, attempt. And secondly, after, in the next semester, from, say, design the world, just design the country is a kind of ideal to do that. It's a bit of a coincidence when you have a new president very soon, and at the same moment to help a little bit, whatever government will be there, and whatever situation will be here, to open our potentials as architects, as students, on how we wish to see the Czech Republic, from small, nicer streets to amazing new high-speed connection to Berlin or to Vienna that is needed to do that, and to acclaim your position in Europe, if not the world. So I invite you also, hopefully next semester, for that. We do that also with more universities, more schools. We work with Arship in Prague. We work with Brno University. We work with Liberec on that, and stage it at a certain moment from here to find like 1,000 voices, if not more, to talk about that. Back to the studio of today and the presentation by the students. Just a word of timing, what will happen. I will speak 2 minutes and then I'm done. There will be, the students will present for an hour and 5 minutes, more or less. They will show how to do that. They do it in a very concise manner, so it's a different, because we know we have a different audience, so it should be almost like a film or like a theater play a little bit in order to get your attention and not to try to fall in the step that we do normally in studios, that you talk long and intensively, also needed, but not for tonight in that way. So that is what the students will present, and they select, and they also the way they present to do that. That will, after that, there is a moment of reflection. We had a group of critics that helped us over the last semester. I mentioned Regina Lukotova from our chief director of art. I mentioned Simon Rozwalka from the professor in the TU in Brno. I mentioned Simon Prokop, who is a teacher here at the faculty, especially in computational science. Lukos Korilla, also from the same department here in the faculty, and Aleš Marek, also part, not a computational specialist, but architectural professor here in the department as critics. You are open, please think about questions. You don't do it for me, you do it for the students that deserve and want some just comments. You can yell, you can laugh, but somewhere in between is the truth that we have to face. So this is an invitation. We do it in 20 minutes because then you are longing for the beers and for the food. So that means that at, say, 8:45, that you can attack the bar in another time. So this is a bit of just to manage expectations, as some of my colleagues would say. Just to mention 3 other people that were so important in the studio. We worked together. Simon Knettich works at MVRDV and as a part of the studio here, is based in Prague, so that we have a continuous input during the process. Javier Arpa is here with us. He's the coordinator of the Y Factory, who did the coordination work so intensely. Adrian Ravon and Lex Delot are not here, but maybe the students say something that they're not here. I saw a competition somewhere in this building to mention their names. That's what it is. Afterwards, it's not only the beer and the food. You are welcome to visit the exhibition. The building reveals itself. That is, which I think I loved it half a year ago, to see all the studios and how they are there. And so the interspace was not there. So the only thing what we did now is do the interspace between the studios. So what you will find is not an introduction only of today's subject, Biotopia, a world which is dedicated to the age of biology that we are facing in order to save our planet. It is also, it helps you to later the studio will be presented here by a film and by the PowerPoint that you will see. And there is a path through the building that goes over the stair, and every floor will lead to a circuit up to the 6th floor, which is a story that the students have been making, and ends in the installation, our studio, at the 6th floor, where again the film will be, the summarizing film will show on that. And in that parcours, rooms are lit, and there you freely enter, and you see how this combination of all this kind of voices of this faculty is celebrated. And with that words, I want to give the floor now to the students. Please come on stage. Don't feel intimidated. They're just watching, and you will have fun.
So thank you, Mrs. Vachova, Mr. Hlaváček, and Vinny for the introductions. I would like to say thank you on the behalf of us, the students, for all the family and friends for coming here today and taking the time to observe what we've covered over the past few weeks and months. It is now the time to take a deep dive into what is Biotopia. Together with Katerina and Barbara, we'll take you through today's presentation, which you can expect to take roughly 60 minutes and a little bit more with the questions at the end. That said, let's kick off. So we are here as part of the global think tank, the Y Factory, which is a research institute that focuses on the development of future cities, and we analyze, theorize, and construct hypothetical solutions of what the future world could look like one day. This semester, the focus was on the Biotopia. When we first encountered the term Biotopia, we were introduced to a series of texts, where the first talks about and elaborates on the hypothesis of Gaia, where the self-regulating system is an essential part of this Gaia, and humans are a key part of. The second urges that our approach towards climate change needs to draw more strategies from the millennia-old knowledge that is all present here and teach us how to live in symbiosis with nature. The third, we learned the importance of rediscovering the countryside as a place for not only recreation, and furthermore, we explored the need to reestablish a healthy relationship between humankind and nature. Lastly, not to forget that from a biological perspective, nothing is unnatural. So then we tried to rephrase what we think about the Biotopia. And in our words, our aim is to propose a series of design inventions with nature that you will later learn are called the bio-inventions. These bio-inventions are here to compensate for the excessive use of the Earth's resources and eventually restore nature's balance. That said, you will now observe a series of hypothetical proposals that are based on a series of assumptions. The way we ask you to perceive this is as an invitation to explore the concepts further and way beyond the scope of our research. To give you a quick overview of what you will see today is the 10 chapters, where you will be introduced to why we need any forms of proposals in the first place, then the strategies of how we tackle our issue, and the application of these set proposals on a chosen scale of our planet. To summarize, you may look forward to a short movie that encapsulates the vision of the Biotopia. So as we are aiming to recover a natural balance on a global scale, we focus on the planet Earth that we know has been around for roughly 4.6 billion years. Over this long period of time, the planet, through natural processes, produced various sources and elements that we learned to use over time. We looked at quite a lot of them through a series of maps that we compiled into an atlas. We start with fresh water bodies, where humankind started to settle. Forests, the lungs of the earth that provide us with oxygen, fuel, and material for shelter. Ocean currents that maintain temperatures across the continents, which resulted in various biomes that provide dissimilar habitats where animals started to settle. Annual sunshine that, together with the atmosphere, provided optimal temperature for life, and together with atmospheric currents and wind, distributed the heat as well as nutrients around the globe. This is all to say that for a long time, the planet has been working in a balance. This balance is slightly better explained through a series of natural cycles. We start with the water cycle, where the water kept evaporating and raining down again, collecting in the seas. The carbon dioxide cycle, where carbon dioxide is produced by the living things in amounts that the planet is able to handle on its own. Just like oxygen, just vice versa. And then nitrogen, which was also present in the amounts that the nature was able to deal with on its own. And lastly, minerals, which will, one day, were only present and being extracted through natural processes such as rock weathering. This is all to show that the planet has been working in balance until a certain point in time, and that is the arrival of humankind. And this is where we move to chapter number 2. So we previously established the existence of the planet Earth to 4.6 billion years. Humankind, on the other hand, has only been here for a mere 200,000 years. So if you picture that 4.6 billion years would fit into 24 hours, or a single day on the planet, humankind is only here for a mere 3 seconds. To bring us to the present times, just this autumn, the population of humankind hit 8 billion. 8 billion, being a big number, is approximately 747 Czech Republics or 467 the Netherlands. This is all to say that the presence of humankind on the planet Earth creates an enormous pressure on the resources our planet has to offer. Over time, the population migrated as resources were becoming scarce and the space too small, which directly impacted the top layer of our planet, the top soil that we use for crops and cattle. It started to take its toll. Forests, the lungs of our Earth, were being depleted at amounts that were really dangerous, while the production of carbon dioxide has been growing ever since, as a result of the overuse of non-renewable resources. Our lifestyles produce a lot of waste that the planet does not know how to cope with yet. And the temperatures have been rising, pushing the biomes away and melting the ice caps, which results in rising sea levels and loss of habitable, sometimes already urban land. So this is to say that one day the planet tries to fight us back. It's just fighting us back, just like the projector. You will have to picture the rest of the slides from now on. Found its way. I'll stay here for now. So this is to say that the planet fights us back. And to give you more specific examples of how the planet fights us back, we should present you the 5 urgencies that we picked from a very long list of many, many urgencies to come in a couple of seconds. But sometimes the energy is an issue in our world, and we need new sources of energy in the forms of batteries this time. We're going to get there. So to further illustrate the scale, thank you very much. To further illustrate the scale of our urgencies, the impact, we introduce you to the 5 urgencies which we picked from the very long list. And we start with the use of non-renewable resources at unsustainable rates, borrowing from future generations, and literally scraping away the surface of the Earth. Waste management being the second, with alarming amounts still ending up in landfills. Just like in New Delhi, where it's directly next to a huge settlement. Environmental pollution, releasing dangerous levels of toxic substances, which in effect change entire ecosystems, just like in this mineral mine in Spain. Access to safe water, which is a problem more significant in developing areas, that is forcing communities to migrate as there is scarcity for water to irrigate the fields. And last but not least, the growing population erasing major parts of the countryside as settlements are spreading. So these urgencies highlight the consequences of the way humankind deals with the Earth. In other words, the presence of humankind undeniably disrupts the natural cycles that you've seen earlier. The hard landscape is becoming uninhabitable for many organisms. Man-made overproduction causes permanent damage to soil. The extraction of non-renewable resources beyond repair eventually borrows from future generations. And overproduction of carbon dioxide is responsible for global warming. Loss of landscape connectivity is a real issue, mostly for wildlife. The increase in water surface runoff is resulting in drought in severe cases and places around the globe. And then last but not least, we are drowning in piles of our own waste as we're struggling to find ways how to safely dispose of it. So that is to say that we find ourselves at a point, at a big moment in history, where we must stop the disruption. And since we are in Biotopia, we must do so with nature. And you might be asking, how do we quantify this disruption? Well, in order to set ourselves a brief to work with, we have to look at global planetary metrics, and that's how we move to the next chapter. We begin with the planet Earth in 2022. To quantify the 5 urgencies mentioned just earlier, we assign them specific metrics they deal with, such as pollution in carbon dioxide or the use of non-renewable resources in the common amounts of energy. However, these amounts are yet very hard to compare as they are in different units. And in order to make them more relatable, we had to find a common unit. And that is why we take a slight detour into the conversion methodology of these units. Let's take energy as the primary example. It is conventionally measured in megawatt hours, and you see the global amount for 2022 on the left side of the slide. We figured you would need 0.1 of meter cubed of solar panels to produce 1 single megawatt hour. And that translates that big number into also quite a big number on the right. That allows, which when represented as a volume, is still quite unclear. So we picked Lake Como as a representation to make the 7 values that will come just in a little bit more comparable between them. The same methodology applies to waste, that is initially measured in tons. Carbon dioxide, that's also measured in tons. Water, which quite luckily for us is very easy to measure in cubic meters already. Infrastructure as a measure of an area, just like buildings, and agriculture, the largest need of all. So now that we've turned these metrics from their original units to something more comparable, we can use it in our research further down. When we stack up the amounts of the different metrics you've seen earlier into a single cube, they're going to figure and they're going to make up something that's 132 kilometers tall at a 35-kilometer base, which when represented next to the planet Earth and a 1-to-1 scale is quite tiny, and even on a close-up or spread out over 3 countries, coincidentally the Netherlands, Czechia, and Slovakia. So we have now set what the global amounts would usually look like for 1 year. However, that does not represent the real issue yet. So we have to introduce you to a concept of the Earth Overshoot Day. Earth Overshoot Day is a conventionally defined term. It states that the planet has a specific biocapacity. That biocapacity regenerates the biological resources we use as humankind in 1 single year. Which when represented graphically before the 1970s, that did not exist, the term Earth Overshoot Day. Because we were able to fit all of our needs into what the planet was able to produce. In other words, until then, we used up less than 100% of that available biocapacity. However, since the 1970s, globally, we use much more of these biological resources, therefore we create the excess. The Earth Overshoot Day in 2022, just last year, falls on the 28th of July, at which point we have used up everything that the planet biocapacity includes, and everything beyond that point is in red in excess. So now we come back to the cube of the original global amounts, which we have now learned is split into 2 parts, the excess and the biocapacity. This is what happens when we speak on the global scale. However, we decided to look at a more specific area and reduce the scope of our research to Prague. And that's precisely where I hand over the word to Bara.
All right, good evening, everyone. So let's first look at the Czech Overshoot Day, which is more than 2 months earlier than the global one, and in 2022, it fell on the 12th of April. Here, we calculated the different amounts of our metrics for Prague per 1 year, shown graphically on the area of Prague and spread out over it. Here are the cubes once again, where the excess makes 72.1% of the total volume of the metrics. We decided to look at even smaller scale, and that is 1 squared kilometer of Prague. These are the calculations in 2022 with the numerical values graphically shown like this in a cube, and again spread out over just 1 squared kilometer in this case. The cubes, once again, where the ratio between the excess and the biocapacity remains the same as for the whole Prague. Now let's look at the comparison of these cubes. So we have the Earth compared with Prague, compared with 1 squared kilometer. As we're focusing on our future, we decided to take a look at how will our data look like in 100 years. The current projection shows that if we act the same, in 100 years, there will be an increase with the increase in population. Here is the volume. Sorry. So, if the biocapacity stays the same, the excess will increase. I'm sorry, I have to go back because it jumped. So, if the biocapacity stays the same, the excess will increase, as you can see on these cubes. To sum it up, you see that if we act the same, the excess will keep growing, but there are ways that we can change our behavior to mitigate this excess. One of which is reducing the intake of animal products in our diet. The data were calculated for this scenario and then were stacked up in a cube once again. Here we have the comparison of these 3 cubes that we just mentioned, with the ratios between the biocapacity and the excess highlighted. By becoming vegan, we reduce the excess, but it is still there. Other behavioral changes include the reduction in consumption of resources, such as water or materials, or sourcing resources strictly locally, and cutting on emission from long-haul transports. However, changing our behavior is not enough, as it reduces the excess, but it does not get it to zero. There are countries, such as Benin or Jamaica, with low excess, and therefore the overshoot day is later or none. These countries tend to have low GDP and high poverty rate. Almost 80% of people in Benin live on less than 5 euros per day. So is this the only way to get the excess to zero? What if we reduce the excess with nature? What if we could replace the excess cube with a biocube? In order to do that, we need to invent. Which brings us to our next chapter called Bio-Inventions. First, we thought about various things that help us tackle these problems already. These are existing human-made inventions such as solar panels or electric cars. However, all of these inventions are artificial, and their production or destruction keep disturbing our cycles. To solve this, we came up with our own bio-based bio-inventions. We put them into a catalog, which we have organized based on their materials, on the metrics that they tackle, and finally, there is the timeline categorization, which is the one that we'll use to introduce you our 13 inventions in more detail. First, we're going to show you the ones that we'll start implementing now and go more into the future as we go. So the first bio-invention that we have is the surface greenifier. The concept of this invention is based on the fact that we're using vegetation to cover the surfaces around based on their specific biome. This map shows that the biomes today are very diverse. In total, we have 11 different biomes, each identified by its dominant trees or plants. The Czech Republic, with its distinct warm and colder seasons, is found in the broadleafed mixed forests. This biome consists of these 4 layers, and for it to function, we need to stick to all of them. Covering the surfaces with vegetation has many benefits, such as a cooling effect, maintaining the biodiversity, or reinforcing the soil. But the main one that we're focusing on is reducing CO2 emissions. As the Czech Republic produces 96 million tons of CO2 per year. This, in combination with other causes, could result in the increase of the average temperature in the Czech Republic by 10 degrees Celsius in just 100 years if we do not act. To implement this bio-invention, we would cover the surfaces with vegetation, and through photosynthesis, they would absorb the CO2 and produce oxygen. 8 trees are able to compensate for the CO2 production of 1 human breathing in a year. And on top of that, their leaves are able to absorb the infrared radiation, which has a cooling effect. Then we calculated how the implementation of this bio-invention would reduce the excess and how much of the bio-invention we would need to do so. Another example is the algae lamp, which is based on the fact that bioluminescent algae can generate electrical current to emit light. Algae consume CO2 and can help us decrease the use of non-renewable energy for lighting, as lighting represents almost 20% of the world's total energy consumption. This problem is especially urgent in cities, as they use 60 to 80% of the world's annual light energy needs. A variety of microalgae can generate electrical current when photosynthesizing that can be used as a power source. These algae need solar energy to emit light. They're essentially tiny individual lamps powered by a solar cell. They recharge during the day so they can emit light throughout the night. And this is a comparison between how many meters cubed of CO2 emissions is produced due to traditional lighting and algae lamps. By consuming CO2 in photosynthesis, algae would actually make this number negative. And again, the excess reduction and the amount of the bio-invention needed. Now let's move a little more into the future, 100 years from now to be exact. The next invention is quite an important one, as it represents the megastructure that we'll live in, the mycelium megastructure. First of all, mycelium megastructure can reduce the construction of buildings and densify. It also reduces the waste from construction industry and CO2 emissions connected to that. Being a great insulator, it can also save energy used for heating. In 2022, there were almost 500,000 of buildings constructed in European urban areas. Mycelia are essentially fibers of fungi that can grow on substrates to form composites. This megastructure will have the ability to regenerate itself by regrowing, and it has two important features. The first one is porosity, which, among other things, allows the daylight to come in. And the second one is the fact that it's adhesive. Therefore, it acts as a natural glue, and that makes it durable and resistant. Mycelium megastructure will also densify our population, as more people can live in it thanks to its structure that can be very high. This structure is characterized by a lot of pores and cavities, which create a lot of space to occupy. At the same time, they efficiently distribute the vertical forces. We can reinforce the structure using spider web, which could be used to reduce its total volume as well. The strand of a spider silk is made up of many tiny individual strands, as you can see on the picture, and in the end, it's 5 times stronger than steel. We would need this much of mycelium to reduce the excess in the volume of buildings. To tackle the need for clean water, we came up with a water-retaining sponge. This is a porous, self-sufficient, and self-grown organism with retaining and purifying capacities of water. This bio-invention would increase the access to safe water, limit droughts, and prevent floods. According to statistics, 1 in 3 people do not have the access to safe water, which you can see on this map. Sponges are also great at accumulating water. In fact, they can accumulate up to 14 times their weight. Thanks to their pores and channels, they can easily filter the water. And here, you can see how it will work. We'll use the water from precipitation. The excessive water will be retained inside, and the pores and channels will filter the droplets that flow through it, making it potable. Again, here is the excess, reduction, and the amount of the bio-invention needed. In order to collect this water, we would use a water-collecting spider silk, as it has the ability to capture water from the air. The reason behind this bio-invention is simply to collect more water naturally, and also it can reduce waste instead of using plastic pipes, for instance. So how does this work? Well, the silk forms rough textured bumps in contact with water, and the structural difference creates a difference in pressure and energy that drives the water to the bumps, creating distinct droplets. In the end, 1 gram of spiderweb can hold up to 160 grams of water. This is how much water from the tap we would save if we collected with the spider silk. The next bio-invention is a special pigment combination which can harvest energy from the sun. This bio-invention represents a more effective way of utilizing solar energy and also saving the space that the solar panels would take up and reducing the waste from them. To power up Prague for just 1 day, we would need 37 kilometers square of land, which equals to the 27 times the old town square. We found a special pigment molecule called xanthopterin, which can harvest solar energy. The yellow stripe of an oriental hornet is made from pinhole depression, which contain this molecule. So the solar energy is absorbed by the xanthopterin and then produces electrical energy. This pigment will be implemented into our megastructure, turning its surface into a big power plant. So this is how much of the pigment molecule we would need to make up for this much solar panels. And here we compare the cubes once again. Photonic crystals are nanostructures found in animal skin that can either reflect or absorb the light. These crystals can decrease the non-renewable energy that we use for lighting, and on top of that, they can store the energy and bring natural light to indoor places. The energy needed for lighting demands in Prague makes up to 496 gigawatt hours per year, which equals to the production of 83 wind turbines. So photonic crystals can either reflect or absorb the photons depending on their wavelength. In nature, the reflectivity is the most common, and it causes the skin coloration of many animals. In our Biotopia, we would actually use the absorption of the sunlight, as the photonic crystals are able to imitate certain wavelengths of light with their structure, allowing us to transport the light. By covering parts of our outside structures with the photonic crystals, we could transport photons directly into our indoor places. And again, how much of the bioinvention is needed to reduce the excess? The next bioinvention is called mycorrhizal network, which has the ability to connect fungi and plants. This network could reduce the infrastructure needed to provide nutrients and water and transfer or store CO2. It therefore connects the ecosystem. The principle of the connection lies in the symbiosis of fungi and plants. The plants provide the substances and information while the fungi transfer them. This will work as an interconnecting channel through the whole ecosystem. But how to understand what is going on within the network, we invented the elastomers that work as biosensors. These would provide us with the visual information within the network, transforming its form in reaction to light, temperature changes, and other conditions. And as a further step, we would be able to connect to the network ourselves with the biochip, for example, like in the movie Avatar. Here we have the cube comparison once again. So the next bio-invention is called indoor biofarms, which will be integrated into our megastructure. Nope. So these indoor biofarms will be integrated into our megastructure, and we're inventing them mainly to reduce the agricultural land, which nowadays uses almost 50% of the habitable land. Another half of that is used just for growing crops, as you can see here. Because of this, we are losing the nature, and 24,000 species are at risk of extinction. The whole world produces 4 billion tons of food per year, which equals to the weight of 18,000 cargo ships. So, how does this work? Well, we were inspired by the hydroponic farming principle, which is based on replacing soil with nutritious water. Hydroponic system is actually 30% more effective than growing crops traditionally in soil, But how can we push this further with our investigation? The Earth provides us with sunlight, fresh water, oxygen, and other nutrients, and all of these can be distributed by our previous bio-inventions, the photonic crystals and the mycorrhizal network. Thanks to these bio-inventions, the crops can photosynthesize and grow inside, which allows for the indoor biofarms. These will be implemented into our megastructure, and in the end, we can save up a lot of soil and land needed for agriculture. Here you can see graphically how much agricultural soil the indoor biofarms can save. And now I'll pass the word to Katja, who will show you the rest of the bio-inventions.
So, hello everyone, and now let's move further also in time scale to 500 years and beyond. Starting with the bio-invention of regenerative flexible structure. The main reason we invent this structure is to reduce production of waste as well as reduce the build-up space or consumption of CO2 emissions. The problem is that nowadays the construction sector is responsible for almost 33% of the total waste. Okay, sorry. And this map shows us the comparison of countries and their production of waste per day. Focusing on Czech Republic produces the same amount of waste as is the weight of 11 Empire State buildings, which is quite a lot. When inventing this structure, we got inspired by a 3D printed material invented by Nery Oxman. Regenerative flexible structure is flexible in its shape. It works on a similar principle as plant does, such as phototropism, so it could provide shade if needed or also regulate temperature or humidity. With addition of water, the structure becomes malleable, which provides us with bigger adaptability. As a further step, after the biochip will become part of us, we would be also able to shape the structure into shapes we need to. Another water-related feature is the decomposability, where heat arises as a byproduct of the process. It is possible due to the addition of chitin and cellulose, which nowadays we can find in a shrimp shell. The regenerative feature is possible due to the addition of bacteria. And the overall effect of this bio-invention is that we can save up to 20 cubic meters needed for a room construction if we use the regenerative flexible structure. Moving on, another bio-invention, we would like to introduce you the cloud generator, which we use mainly to regulate the humidity, but also to reduce UV rays and regulate temperature. Keeping the ideal humidity, which is between 40 to 60%, reduces the spread of droplet-borne diseases. But to regulate the humidity, we need to understand the cloud formation first. Firstly, we need two particles, particle of H2O and aerosol particle, that altogether create water droplets. And amount of water droplets create clouds that humidifies the environment, for example, through the rainfall. But how to push further this already well-known principle? Well, we tried to put together plants that drops an excessive amount of water, such as Calla lily does, with microalgae that emits particles of aerosol. Growing them all together on the mycelium megastructure, we get the water droplets that then condensates and forms clouds that cools down the environment. Another invention we would like to show you is called noise utilizer, that reduces and utilizes noise pollution as well as produces renewable energy. Because the world nowadays generates over 66% of the electricity from fossil fuels, so what if we use the noise as an electricity source? The noise of 70 decibels, which equals the background urban noise, would light up one 12-volt light bulb. It is possible due to nanocellulose that works as a biotransducer layer and also because of mycelium structure. The principle is that the mycelium could absorb the incoming sound to its pores, which then are transmitted to the nanocellulose layer. In a bigger scale, thanks to this principle, the sound is transmitted to electrical energy that could be stored or supplied back to the city. The overall effect would be that 1 meter square of the noise utilizer is able to light up 500 light bulbs. And the last but not least bio-invention is called transportation bubbles. We use them mainly to reduce infrastructure because nowadays infrastructure on the earth shattered it to more than 600,000 fragments. And focusing on Prague, transportation takes 10% of the whole Prague surface, which equals the same amount as forest covers. So simply, when we reduce the infrastructure space, we would save up the space needed for the wildlife. In order to free the space, we would replace the transportation system with transportation bubbles. So what if we use yield electric cells for creating a membrane that powers up the transportation bubbles? Because electric yield produces the same amount of jolt as one socket does. So using this principle, we would line up particles of salt water, fresh water, positively charged particles, and negatively charged particles to create an electric jolt. These jolts would create an electricity generating membrane that is filled up with hot air to make the bubble fly. These bubbles could also flock due to electricity in its membrane, and as the evolution of them goes by, these flocks could also merge into bigger bubbles that would be able to transport almost anything. And these bubbles would draw its nutrients from the mycorrhizal network. All these bio-inventions together form a biocube. And the biocube represents specific number of bio-inventions to neutralize the excess. And these are the specific quantities of each bio-inventions we have to apply. The biocube consists of complex blended bio-inventions. But how do we apply this complex system? How do we analyze it? And how do we visualize and simplify it? Through voxels. You might be asking, what is a voxel? Well, according to Oxford Dictionary, voxel is a three-dimensional space consisted of elements of volume. The voxel we work with is a cube of 3 meters on each side. The voxels allows us to quickly determine the volumetric data and compare the differences of otherwise very organic innovations. In other words, with sufficient density of them, we would create an organic impression while being able to easily analyze them. Through the usage of voxels, we are able to count how many of them we need to reduce the Prague excess. And this amount of voxels we are distributing on 1 kilometer square of Prague on a voxelized model. Now we would like to show you the principles of distribution, starting with the surface greenifier that is distributed on places with the highest concentration of air pollution in Prague. Moving on to LG lamps that are evenly distributed along the streets and in public areas. The water-retaining sponge that is placed on shaded areas where the sun exposure is less than 5 hours a day. The clouds are generated on the places that are overheated to reduce the direct sunlight and the heat islands. The mycelium megastructure is a growing, highly dense structure for the future increasing population in the cities. It creates new surfaces for placing the new structures and volumes for living and growing food. It grows out of buildings that are abandoned or destroyed. The noise utilizer is distributed on the places that are mostly polluted by noise. Pigment electricity generator is distributed on the sunny places, mostly rooftops, and its shape leans towards the sun to absorb the most energy possible. Indoor biofarms are placed inside of mycelium megastructure, as well as photonic crystals, mycorrhizal network, and regenerative flexible structure. And ending with transportation bubbles whose position depends on actual needs. In the end, we are applying all the distribution principles as layers of the new biodiverse matter we call biomatter. Biomatter is formed by the blend of all the mentioned layers, with adding the mycelium megastructure with pigment on its surface that is then distributed and absorbed as energy, with rebalancing the cycles of nitrogen, phosphorus, and carbon, using the power of sunlight as well as the water cycle, and releasing pressure on the soil with change of transportation into the air. Now let's have a closer look on the flow of nutrients within the biomatter. We can see the flow of the water cycle, which is part of the biomatter, while the outside environment is left for the wildlife. The particles and nutrients are distributed also within the biomatter's interior. These smaller cycles of light, water, or energy are visible on that section, as well as the system of growing food in the indoor biofarms based on the hydroponics principle. All these small cycles form one big rebalance cycle within the structure of biomatter that creates a whole new city principle we call the sponge. But how would we live within the sponge? How would the life look like? Well, firstly, we would live in a more adaptable environment. The sponge would be able to react on the space needs. It would grow more on the places that are more required, and it would shrink on the places that are not needed so much. This feature is also affected by the biodegradability. Let's see it on an example of classical building versus the sponge. Both of them could somehow react on the increase of the population density. But due to the biodegradable feature, the sponge would easily adapt on these changes, while the current state buildings could only decay, resulting in a bigger construction waste. The shape of the biomatter could also react on the outdoor conditions to provide more livable environment. In the warm weather, the surface area to volume ratio of the biomatter is bigger and also creates pores for better airflow. While in a cold weather, the biomatter creates compact layer allowing the sun to come in. Both of these principles ensure pleasant environment within the sponge. The reaction on outdoor conditions is also provided on smaller scale of photonic crystals. They lean towards the sun so they can absorb the most energy possible. And the last, final selected part we call connectivity is provided through the mycorrhizal network we are connecting to with the biochip inserted into us, so we can influence and shape the environment we live in according to our needs, so we could connect between each other, but also connect to the whole ecosystem of the sponge. Now we would like to introduce you our film we call The Life in a Sponge.
So we have to wait a little while the video loads up. But in the meantime, over the semester, we were thinking, I think everybody was thinking, what your apartment would look like in this sponge. Because the sponge, it sounds quite alien. Well, it's very difficult to say, and you will see it in the video in just a short while, and I hope that short while is very, very short. But maybe the fridge. Is the fridge going to be part of that mycelium structure? How do you make your coffee in the morning? Is that coffee going to grow on the outside of that huge sponge? How are we going to travel? Well, we saw that one of the options is the flying eel bubbles. And we had so many of these questions over the course. But I think the best way to leave this is to leave you with the video that will come in just 2 seconds.
Earth is our home, born 4.5 billion years ago. For thousands of years, a place where humankind lived in harmony with nature. Biotopia is about bringing that balance back. Let's imagine Biotopia in Prague. Let's imagine a 1 square kilometer changing through a blend of bio-inventions. What if all the bio-inventions turn into a single substance? A true biomatter capable of meeting all needs of both humankind and nature. What would it look like? The vision starts with the transformation of neglected buildings and continues with the rest of the city. These buildings serve as the perfect nests for this biomatter to start evolving. The pipes of the buildings distribute fresh water and nutrients for springing plants. The first step towards this biological future. Not only greenery will take over buildings. The biomatter starts to disintegrate the old artificial piping system and substitute its function. Fresh water runs through the pores of the biomatter, essential for life of any kind. Slowly, veins of the system become a key support for all organisms thriving in a newly established symbiosis. When the greenery starts to accumulate, CO2 levels will drop, and cooler and more humid urban spaces will form. Perfect conditions for biodiversity to rise back again. While the plants are supplied with water and nutrients, the products of photosynthesis are shared with the biomatter in return. Water is distributed through biomatter pipes, but it needs to be collected first and stored. Therefore, even in times of drought, water retained in organic collectors can be provided. Enjoy the first step towards Biotopia. Any balanced ecosystem cannot be complete without its fauna. We aim to create an environment in which we, humans and animals, can live side by side. Starting from the interior of the building, the biomatter is expanding, forming the very first pillars of organically shaped city sponge. Due to this process, the form of our houses will need to change drastically, opening new possibilities for design. First bio-inventions are integrating into the sponge. Among them, power plants that can harvest energy directly from the sun, thanks to a special biological pigment. They are growing on the surface of the structure, with the ability to change their shape and orientate to achieve maximum sun exposure. As the pillars grow bigger, bridges are emerging, allowing for fast connections across the city on multiple levels for humans and animals. Thanks to greenery densification, water evaporation increases. This increased humidity generates cloud formations, which we can use for cooling overheated areas. During our lives, the sponge grows and shrinks, bends and twists, clusters and scatters, adapts to our needs. It can become porous to increase wind flow for cooling. It can soak up excessive water from floodings, or it can move whole neighborhoods to fulfill residents' urban desires. The backbone of the entire sponge is the rich mycorrhizal network within. It distributes water, nutrients, light, and information, creating an integrated ecosystem throughout cities. This network becomes especially crucial in underground farming. It brings all the water and nutrients the farms need, but also natural light, which is emitted from photonic crystals. This way, the biomatter can serve as soil and produce food fully locally, decreasing the need for transportation. This contributes to the self-sufficiency of the sponge on all levels. Interior spaces have now fully integrated the bio-inventions. Furniture is made of regenerative material for the ultimate reuse, thus saving tons of waste and production energy. The combination of the lush greenery, the form of the sponge rich in cavities, and the sufficient amount of resources creates an exciting and flexible multi-level environment for both humans and animals. Eventually, the regenerative material will not only form new structures, it will also form new relationships. In a matter of seconds, you can make a wall disappear, joining spaces with a group of friends. You can adapt your environment and form a new bar to gather around and cook a dinner together, all through the real-time communication within the mycorrhizal network. Meetings have never been easier. Bubbles, based on electricity-generating eel cells, provide a new means of transport. The system is highly flexible, as its elementary units are able to form flocks of various shapes and sizes. Even the darkest parts of the sponge appear calmer and safer. Zero-emission lighting is provided for the entire city by lamps based on algal bioluminescence. The biomatter is a fully biodegradable medium, providing resources for all life forms of the planet. It can move and reshape instantly in response to the needs of humankind and the Earth itself. The sponge is now expanding from local cities to regional networks, across borders and entire continents, eventually forming a new three-dimensional Earth crust. This is the dawn of a new era of biology. Welcome to Biotopia. Earth is
That's just closing. There's a couple of closing words from the presentation still before the. And before we let you go, we also have a couple of closing words. I hope you enjoyed the movie and actually found out what the future world of Biotopia means. I certainly did. So to reiterate what we introduced at the very beginning, we aim to propose a series of bio-inventions with nature that you know are now bio-inventions to compensate for excessive use of the Earth's resources and restore nature's balance. We have witnessed the hard consequences of our presence on this planet, which we use as the starting point in our research. We have described how we use these resources in excess, and that this excess turned into our target to solve. So you might be asking if we've achieved it. Well, we say that on a selected scale, which in our case was Prague, and with a number of assumptions, we, in some form, have. In the form of a complex ecosystem of blended bio-inventions that we call the sponge. We have learned that to come up with the bio-inventions on their own is not sufficient, and that we need to blend them together into what we call the biomatter in order to unleash their full potential and use their entire effect. In many ways, this comes back to the concepts that we introduced at the very beginning through a series of quotes, that we need to become a part of a self-regulating ecosystem to draw from millennia-old knowledge, and in short, live in symbiosis with nature. And I think today, more than ever, we know that we can't really rely on solely technology. So we urge you to remember that this is our utopian vision of the future that is yet to come. It is, in short, our design vision, to which it is essential that we add input from multiple professions to kickstart the fruitful cross-pollination of expertise, and therefore, one day, hopefully, produce real-life and applicable solutions. In short, our research is only a small fraction of what the future can become, and potentially include the role of society and culture within Biotopia. For centuries, design focused on objects with single meanings, and that's when everything was architecture. More recently, we zoomed out to look for new meanings at every scale, and everything became urbanism. Latterly, design has finally started to timidly understand the concept of green, and that's where everything became landscape. But today, more than ever, everything is nature. And we welcome you to the era of biology. Thank you. one last thing, we would just like to say that it might not be obvious, but this is not just the work of the three of us, it is the whole team. And with that, I would like to invite everybody who is part of the White Factory to join us on this stage. If you can come over, we have some deals to deal with. But nothing bad. And of course, this involves everybody. So, Vinny, Javier, Shimon, can you join us as well? I think we have something for you. Somebody has.
We would like to thank you for the semester.
So we had a great time, and we would like to thank you and present a couple of gifts. And that's all from me. Thank you very much. And now we move to the discussion, I believe.
This is a new raw color. This is a new raw catalog that is needed basically in architecture to fundament. I thank you for that. This is a surprise. One thing to say is that the film Avatar needed about like 100 times more of people than you did. So that is, this for me it's emotional to see what that say in order to get some kind of width. Let me say it that way. That is also felt. I imagine anyway for me when I see the work. I have to explain that I haven't seen this last presentation. We met each other last week again, and then on that space, and you said, "Go away," because we need to work. So no extra input was needed at that moment to deal with each other, and that has led for better and for worse to a certain kind of attempt to be cohesive. I think it's nice to give some of you the word in a way to simply react, whatever it is, and to do that. I mean, I can ask you for that, but that's not my role at that moment. So maybe I should ask, of course, Dalibor. You got me in. Well, do I have to leave Czech Republic now, or?
We will discuss that later. Well, first of all, I would like to congratulate you for the great work. I'm really very much impressed. Okay, I'll start with the questions. Your research, the way I understand it, reacts to the growth of population on Earth. Do you think that's the only way, or is there any limit to this approach? That's my question.
Who wants to answer from the students?
In short, can we grow with another 60 billion people? Oh? Yeah. Somehow the attempt of these calculations of the block that is needed, the tower for the Earth, and the small Pisa tower that the planet needed. So in the case, can it grow? Can we add capacity? That's the paradox that's in the question of Dalibor. Or is it too hard? Let's give it a try. Any tries? Or didn't you expect this question?
No, I'm sorry. Actually, I have to ask whether you're asking us if there are any other limits, such as the population growth, or if there are any other solutions to it. Sorry, I think I didn't understand it.
If there are limits to the population growth.
Oh, if there are limits to the population growth.
Or way how to limit the population growth, maybe, whatever.
I'm still not sure I'll understand it correctly, but basically the Earth is the limit of population growth, so.
There were multiple scenarios that we tried to discuss in the studio, but it isn't only about the population growth, but I think also about densification of the cities, which is, for example, we were thinking about like, what if the whole Czech Republic actually moves into Prague? What is the density change then? So it isn't just about the growth of population, but what if, for example, the whole world wants to move to Europe or wants to move somewhere where it's nicer to live?
But I love the question. One, to say, always after a presentation, always people ask what's next. They are always intrigued to, so give this a space. This is kind of fair that you do it. But imagine indeed that this, if it's possible to construct on the base of solar energy, basically, and of the kind of recycling process of water and minerals, if we can speed it up, then we form maybe a flocking enterprise that is bigger than the planet Earth, and that is maybe encapsulate a circle around the sun, or another kind of sphere around the sun, to extrapolate that. You cannot solve it today. I want to defend the students. So the question is very helpful in terms of pseudoscience, or in terms of research that needs step by step, that goes from one to the other. You created basically you created this question. That is the nice part that I want to defend you, that you cannot immediately answer that question. But yes, as a teacher, I can see, wow, good question for our next studio to imagine, to see how the capacity of your principal inventions have been done. So can you excuse the team that they cannot solve it right now in one studio? You had too many side exams in this in the studio. You pull them too much away from this subject.
Okay, we'll postpone the question for the next semester, maybe.
Simon, you have been here also teaching with us a little bit. Now you see, say, a result.
Wow. Thank you. I am happy to be here again. And I must say that there were a moment that I had a lot of suspicions that it's not too good. But then I noticed that it's something together with the movie Don't Look Up, because you look a bit crazy, the same way that DiCaprio was. But at the end, you show the biggest problem maybe for architecture, the one we should work with, and thank you for that. And I hope you will not go back to the traditional way of thinking about architecture after this studio. And I also hope that this will change, maybe, the discourse at the faculty here and maybe in our faculty in Brno as well. So this is the biggest impression for me. Thank you.
Someone wants to react on this? Can you understand what Simon tries to say? That you don't give up.
Well, let me give some time.
Don't feel intimidated.
Yeah, I think the main thing that this studio gave me is the way of thinking. It's not the product, maybe. It's the difference in thinking comparing to other studios, maybe, and it gives like another level of purpose to architecture for me. So I'm grateful for this, for being in the studio. So yeah.
That's a beautiful wording in that way. I mean, there was one. My teacher is also in this space, so I have to ask Tanja, what you have seen this? Did I still have deserve your diploma that I got from you?
No, it is a wonderful exercise. Really, my big regard for this, and I think it's very good teaching method, because it's not about the result; it's about the process, and it's about the way of thinking, and let's say. Of course, all these variables could be different, and you can choose different strategies, and you can go different way, but very important is that you learn to put essential questions which go over the border of architecture. And I recognize something from your work as you were a student, but this is much better. And I think it's a big impulse for the whole university, because these kind of questions which go beyond the border of architecture should be answered also by other faculties. So it would be wonderful to find the way how to involve other faculties which are, of course, interested in the same questions, but they look for very different answers. So my congratulations, Vinny.
I enjoy, yeah, thank you. It's, you can see it as a kind of excuse that it should go out of this faculty, but it's true. We have to ask our engineers to construct differently. We have to ask our biochemical engineers to work better. And so some of the questions you have been asking already to it in order to escape from the existing. That's what I learned from it. I have no clue how the university here works, if that's doable in the bureaucratic existence, basically, of or existentialism that is in between the faculties. It's a bit hard, and not only here, also in Delft, but it would be wonderful if there could be a plea or a plid to the super dean of your campus to find some kind of collaborations of asking questions, giving hypothetical answers. Not a research yet, but only this kind of that I pick from you. I'm looking for two contributors also in this enterprise, but maybe they have gone. Regina, you pointed during the process on make things, make designs. Is it a design?
First of all, yeah, thank you for your great work. We have heard now the words as result or product, and also that the product is not important, but the way which leads there, it's of a great importance. And I love the shift actually between the analytical part and your product, because it's always a danger that one can drown down into analytical part and analyze endlessly. And what the result I've seen before Christmas, the design, the product was still missing, but I'm very happy that I have seen it today. And could be 1,000 other ways how to get there, and 1,000 different visions and products, and you design one of them, and it's of a great importance and inspiration too. So thank you, and I have no question for today. So you asked me, yes, great product, I would say. Happy for that.
Thanks for the not asking questions. I go further in this mini tour around it. We had great computational help, and in this to understand complexity. Sometimes architects cannot do it, and at a certain way, the logics of structure, logics of thinking, which is constructed in your department, was of a great help to do that. So it is, and probably is tons to do. But do you have any advices, having seen this?
I actually have a question, but advices like, yeah, whoever done all that scripting, good job, guys. Like that's all, like all the analysis as well, awesome. Really thank you for the final touches. It really came together since the last presentation, as Regina said. But can I have a question? The mycelium megastructure grows out of cellulose, right? It eats up cellulose. And there's going to be a lot of that cellulose needed for building actually something which is higher than the cities we've got so far. And I get it, there's some redistribution of nutrients, water, CO2 and so on. But that means you are designing the whole crust of the earth to become something else, just for architecture, which serves humans and also the nature. So I have a question. Did you redefine what architecture is while doing such a project? Because I think you must have.
Any first floor to one of you listening to this question? Who can try to give some glimpses? Did you see this as new architecture? Hard, or I'm looking to it.
Maybe I would say that we find out that architecture is not only about building houses, but also about making inventions. That's all.
I liked your question because I think there are certain moments in time, the last 200 years, and that every moment, say there was a group of architects or an architect or a movement that somehow expressed how the planet should look like. It was in the metabolist time, it was also in the classical time, in the neoclassical time. These images appeared as almost an holistic enterprise. I think Frank Lloyd Wright did it in a certain way with Brodecker, which, as today you have seen, the real images came out in a way very beautifully through the zine. So there is and they express some kind of cultural momentum in time, if you look to this holistic components of it. So you put this into that perspective, if I maybe, what kind of planet can it be? It's also you describe, that could be, and that's what helped also Dalibor's question, how that flocking component of the crust could look like. We have a very existential first question, though. The amount of celluloses that is needed to construct this mycelium element was not in your cycles yet. I don't know where the mycelium group is. Do you want to say something? How much celluloses do you need? Who did the mycelium invention? Is it possible to answer it, or we also need a new studio for that? That's also fine. But I liked it because it's like it constructs these new cycles in a way of how to make the celluloses. So it is quite deep. You tried the little pieces of that reality, of this kind of construction. Of course, it's hypothetical, and you need a lot to do it. But exactly that kind of questions are nice to have on board in order to calculate the amount of celluloses to deal with it in that growing matter. Are there more questions like this, like constructive of any nature? I went through a little bit to different speakers in our platform, but please. Okay, one moment. Yeah, fair enough.
Thank you. So I would like maybe answer the question if we redefine the architecture, and I don't think so, maybe for me, because I think we are doing still the same thing as other architects did to this day, and that's just designing how we live and where we live. And I think we are on somehow journey where we found out new things, but it's basically maybe just the same thing all over again. And I like it. And I think it's actually nice to somehow still be on this journey with the other guys from history. So that's maybe just my opinion, but I don't think so. I think we are just making some new clever ways, and that's it for me. Thank you.
I think it's a beautiful observation on the word prehistory, because this is what is somehow now you make a kind of an introduction to what happens after history, and then you make it prehistory. Well, it's just a word game. Don't forget. I saw your question. That's.
Thank you. First of all, I would like to say that I was not wowed by the latest avatar, but I was wowed by your presentation and your research today. It was really amazing. Thank you, guys. And my question is quite simple, maybe similar to the gentleman on my left. You were considering using spider webs. would you produce somehow artificially those spider webs, or would you grow spiders to produce those spider webs? How would you do that?
Who's the spider king or queen here? What do you need to make spider webs? How many? How do you?
I'm really not sure how to answer the question, but when we were doing the research, we also, of course, doing the research on the ways how now they are doing and how they are using the spider web right now at the moment, and that's the artificial way. So they're using it, and some kind of the spider web can be even like harder than a steel, so that's how it. But of course, in ideal Biotopia, it would be perfect if we have like some maybe biologically modified spiders who can like actually do this our spider web by themselves. But it's really hypothetical, and I couldn't answer it like in a moment. So, but.
No, imagine that's because I like the question, same as the mycelium question a little bit, is in order to understand what you propose, you have to say how many spiders you need. That's what. And the spider farms add to your cube. The danger of spider farms is that they escape. And then how to deal then with them. So nature at the moment has given habitats to restore that. So you have to have a multiplier in that spider factories to create that habitats in a way. Just a glimpse of what a possible answer could be in the next studios to paint that structure. If you do that for everything, you did it now for 20 subjects, basically, and if you have this kind of line, this pyramid, basically, of food, that's what you suggest, overlapping over each other, and if you do it maybe for another 100, wow, it's insane. But the beauty becomes better. And you can distill from there what you need on a nanoscale to solve it properly. So that it's a mirror world what you paint, because it's exuberantly big that we then need for this new ecology. But you can help to get a kind of compactized version on it, like we do at the moment with certain drugs or certain kind of how the world of pharmacy is also compactizing what you say. So that is, again, there are models of compactization to get rid of the spider farms, to get it into a production line, as you suggest, indirectly, is what I could imagine. So I'm happy with the question. These are the things exactly that for me, as a teacher, I need to make things deeper. And for you, as students, to learn from, say, you achieved something, and yes, there are always white holes, say, and pockets of knowledge that are not yet there. So that's consistent and endless in its construction. That these questions are showing in that way. I would like to give one. Of course, you should. How can I not walk to you already earlier? That is. Thank you.
Thank you, Vinny. I must say, chapeau. It's unbelievable what you achieved. First of all, to put all these students into a team that collaborated in this fantastic way. I think that is extremely difficult, and that all of you survived during this process. You, Javier, Adrienne, Lex, and Shimon are still alive and kicking. I mean, that is also an achievement, because you've been flying over from Netherlands to Prague and back so many times in so difficult conditions. But for me personally, the most interesting thing is that we all feel we are sort of living in the last years in dark times. The young generation sometimes hashtags last generation, that everything is getting worse and worse and worse. And suddenly with this approach, there are so many new solutions, new possibilities, a very exciting future. And even if it happens in a different way, I mean, I think the approach that there is a way how to overcome all these difficulties and dark times is a message that we should all remember, and that's what architects and landscapers and designers and everybody we have here are for. We bring the ideas. And I would just want to know, how do we start with the rest of our subjects to go into this direction?
Who should answer this? Oh, it's for me. I think you already started. What did I see? 3 weeks ago, that there was one group that were concentrating on glass, where water was going into it, so that it cools the glass, and that it becomes a device, almost like a trauma wall, but then in glass, to combine light, view, and not only with overheating, but also with dosed or dosated. So one could say that maybe it could be nice for a school to suggest one semester that everybody tries, every studio, somehow find paths like this, how products can be improved, how spaces can be improved into even a more sustainable direction. And there are steps by steps for that. I think the students did already an inventory. We are aiming also to, in the book, to show current inventions that are as an introduction on that. And it could be a wonderful festival to imagine that. And then if there is a design show somewhere here in Prague to show all these kind of inventions that are already happening in that direction, and more to come, and the fantasies that could be connected to that. So that's one answer to your question. There are glimpses in it. If I walk around, I see the landscape group made already beautiful water catchment areas. That's part of what this group is also doing. There are villas that have other kind of material with tomba walls everywhere to catch that. And that's that turns into another kind of Tugendhat at the moment. I'm fair with that. So etc. There are glimpses of that. So that's what I would say. But it is maybe smart for a university to pronounce yourself a little bit more on that. To say, okay, we already do something. Contribute to it. That is what you maybe could do from your, let's say, the second floor, to sometimes help on this. That would be. Does it then harm the liberty of researchers? Or that is a question, because everybody has his or her agenda also in it. Or is this like a moment of talking together to make that possible? I hope so. And are there more frames? This is a frame. And there are more. Yes, there are. The social frame, some of you said that in the end, is also not completely engaged in this. So it is. It could be a fantastic academic statement if you would work on that. And I missed that in Harvard. So to give you just a comparison, so maybe it's in Prague after Harvard. So that could be then if you are looking forward to that. Your president would like it. So that's to have that engaged. Okay, last moment before we head to the beer. Are there other questions from the audience or remarks that I can, that would like to do? I mean, we are very open. It's not about, we hope to achieve sometimes some level of cleverness. Don't be intimidated. It's kind of just a talk to each other. And if not, are there moments that you, some of you as a group, would like to say something, or you have said? Yep, I'm coming.
Thank you. So just to follow your idea that you suggested, that this studio follows kind of a different direction than other studios in our faculty, I would just remind maybe more to my classmates the first time we heard what we are going to be doing this semester and our faces, because that was funny. When we actually find out that this is going to be something completely different than we are used to. And that in this semester that we are not going to be designing any building, and that it kind of shaked our ground under our feet, that what we learned here, it's actually, okay, we are not going to be designing a building. Oh, wow, okay. So it was, even for us, it was kind of a experience that we did a research, quite of a deep research, and that we did a scripting that none of us knew. Just so you know that, like 2 months back, no one knows what is the word of scripting, or like 3 people here. And yeah, so I guess that's maybe the main experience we have, that we have this different view on what architecture students can find out in university. And yeah, so I have no idea what I'm saying now, but yeah. Just so that it was, even for us, it was a surprise that what we are doing and where we went, and that in the beginning we had no idea where we are going to end up, and we ended up here. And I guess we did a pretty good job, so yeah.
Well, with that word, I would say the exhibition is opened. Please go there. The bar is opened, and give them another last applause for today.